Hi, everybody. So I want to give you a little bit brief background about myself. So I have a PhD in pattern analysis and machine intelligence. Have over 11 years in data analytics. I work as an innovation lead in intelligent mechatronic systems. I have been recently recognized as one of the most influential women in the world by the IoT, by the Connected World magazine, based in San Francisco. Woohoo, Canada. So, and I have few publications, a little bit more than few, and I'm an award-winning researcher. And the reason I'm giving you this because I'm going to talk about a little bit nerdy stuff, and I want to prep you for it. So, predictive analytics. How many of you have used predictive analytics before? Awesome. Okay. How many of you use Google now? Yeah, a little bit more. Amazon? Fewer, that's weird. Netflix. Yeah, everybody. All of these services do use predictive analytics to better understand what you're going to do next and what do you want to do, get, or buy next. So predictive analytics is the process of learning from historic data what's going to happen in the future. So it connects the current moment with the future action that you might do. But it's very important to classify or understand the difference between different types of analytics, because some of them the differences between them might be blurred. So the first type is descriptive. So descriptive is understanding what's happening at this very moment or happened in the past, just understanding what happened. Diagnostic is understanding why it happened. So why did I decide to remove this? I have no idea, I just did, but why? Predictive is making the connection of what's happening at this moment to what's going to happen next. This connection is key. Because without predictive, we cannot do prescriptive. And prescriptive is the newest and most, and the strongest type of analytics where we can change your behavior or the system's behavior. Tweak it, understand what's going to happen next, and then do actions to tweak it, to change it, to be able to influence it, which is pretty cool, to be honest. So who was following the elections over the past couple of weeks? It was a tough elections, huh? It was different than the one in 2008. Okay, so regardless, in 2008, it was a very, very unique election. And it's not just because Barack Obama came to the White House. One of it because Nate Silver, who knows Nate Silver? Yeah, awesome. So Nate Silver did predict 49 states out of the 50 states accurately. And everyone was talking about the power of prediction. But what Nate Silver did was actually forecasting. He just predicted per state. He looked at the state as a whole and he said, this state will vote Democratic, this state will vote Republican. And this is what he did. But the true winner of the predictive analytics was Barack Obama's campaign. Barack Obama started with very limited resources compared to his opponents. And what he did is he used predictive analytics to analyze how every voter will vote. And if this voter can be influenced to change their vote or not. So they looked into, is he voting Republican or Democratic, or he's not voting at all? And which is better? Because he had limited number of volunteers. He had limited number of funds. So he used this to do something that has been later used for directed marketing, to be able to change and influence the effect, the outcome of this election. And by using the same technique, you have Target, for example, used predictive analytics over directed marketing, and they were able to increase the influence of their campaigns by 15 to 20%. And you have First Tennessee, which is an insurance company, and increased the response rate by 20%. And you have the Premium Bank card reduced their mailing cost by $12 million. All of that by understanding what state are you in. Are you willing to listen and be influenced, or you are decided and that's it? So all of this, so that shows the power of predictive analytics. But that mainly focuses on directed marketing or campaigning. But there's so many applications for predictive analytics. Biggest of which is fraud detection. We all use it every day. This is how they detect fraud in credit card usage or even fraud in insurance companies. You have economical predictions. You have cross-selling. So you know when you see you may also like in Amazon under whatever you're looking at, that's actually predictive analytics. They see what you might like next based on your history and based on what other people did. You have behavior prediction, which is very important in autonomous cars and in connected cars. You have consumer retention, customer retention, as well as medical application. And medical application, this is just one word, but there's a huge umbrella under it. So whether you are looking at how the diseases are going to spread, what type of diseases there are, and even the impact of different types of medication, and people's acceptance to them. So all of this is currently in the market. But also, you have the connected car. Most cars nowadays have some sort of autonomy to them. And they do some level of predictive analytics, and it's expected to grow extremely high in this field because they need to understand what's happening next. And as we change, as we move from the concept of car ownership to the concept of car sharing, like Uber, Zipcar, all of that, this needs to work with us. This needs to take that into account. Predictive analytics needs to take that into account and propose to me the right modality based on the time, based on what I want. It needs to understand where I am in terms of state of mind. And of course, this has a direct application to autonomous cars. Prediction not only of what you're doing, but what others are doing around you. And all of this is fueled by big data. So all of this is very interesting, and I think I'm excited about predictive analytics. But the question is, okay, so what can we do to get this happening? We have some models of predictive analytics that work with some data, but how can we make it all the way to autonomous cars? I want my autonomous car. I want my car pod. Well, this is where the power of deep learning comes in. So how many of you have read, heard, or did some work on deep learning? Yeah, few. Okay. How many of you have read, heard about AlphaGo? Sorry. AlphaGo, that won in the ancient Go game. That was huge, guys. That was huge. This work was not predicted to happen except for few decades to come. We were able to do it today. We live to see that. This is a very complex game. So before, AI used to win, or at least play on the bar of the best chess games, or with the best chess players and all of that. But Go was a very, very complex game. So many different variations. And just having this to be trained was something that we considered undoable at this point of time. But just in March 2016, this year, AlphaGo was able to win. Okay. How many of you use Siri or Google Voice or all of that? All the new speech recognition systems are actually based on deep learning. And that's so cool because there was a huge leap between the first version of Siri to today. They're actually, in Google now, they were able to have 30% error rate, error reduction since they started using deep learning. 30%. This percentage of enhancement hasn't been done in 20 years in speech recognition. And also for Google Voice, for the transcription of voicemail, they were able to reduce the error by 50%. That's a lot, 50%. In research community, we talk about 3% and we think that's an achievement. I think, how many of you do research? Oh yeah, few. Hi guys. My type of people. So, and computer vision. So, I am sort of excited and a little concerned to say that using deep learning, they were able to have better, equal in bar, or even better than the human accuracy for detection of images and understanding of images. So there's this huge database called ImageNet that have about 1 million images in it. And they were able to achieve better than human in detection of what type of image that is. And even natural language processing that we thought were so awesome in, they were able to get like huge improvements just using deep learning. So the spam filters in Google get 99.9%, 99.9% of spam with only 0.05 false positives. That's amazing. So, okay, so there's a huge hype on deep learning. So let's try to understand, is it real or is it just a hype? So first question is, what is deep learning? So deep learning is a machine learning approach that tries to drive meaning from data using a hierarchy of multiple layers. And this is a key. The key is the layering in there. It's exceptional at detection of patterns, especially when the pattern, when the unit itself doesn't have a meaning, like a pixel. It has some sort of number to the color to it, but the pixel itself doesn't tell you much. Same for a word. A word in itself doesn't tell you much, but an aggregate, a group of these pixels or a group of these words can tell you a lot. And deep learning was able explicitly to capture these patterns from these small, non-meaningful units. Okay, so why now? So, okay, so we had neural networks since the 60s. Why today? Why is deep learning impactful today? We had it from the 60s. Couldn't we figure it out earlier? Normal question, right? Well, today we have big data. We are more conscious of our data and our data resources. We have impressive computational power thanks to Moore's law. And we have huge algorithmic advancements. So all of that enabled today to be a good day for deep learning. So, okay, so deep learning, it's exciting. So let's see numbers. Why is it really good? Because if you look at speech recognition, and this is since the 90s, you can see the trends. This is unprecedented. The reduction in the error rate is unprecedented before. The slope of this curve is very impressive. If we look at the ImageNet that I was just talking about, we were able to get better than human performance, superhuman performance. That's amazing. And this is something that was very unique to humans, our ability to understand images. It was very unique to humans. Okay, so why is it doing so good? Well, deep learning do work like humans' brain does. So if you look there, this is exactly the layers by which your neurons fire when you start seeing an image. Initially, you start looking at the edges, and then you start looking at the features, and then you make sense of the features, and then you combine all of that to define that this is a cat. So if for my 5-year-old, when she was about 1, if I show her a cat, and I tell her like, see, the cat has ears and nose and whatever, and then I show her an elephant, she will start comparing the images in her head to each other. And maybe the first time she's gonna say by mistake, oh, maybe the elephant is a cat. But as soon as I point the trunk out, that's done. It's one-shot learning, right? That's the power of human brain. And they were able to capture that in deep learning. So by having the multiple layers, they were able to get different layers of features and abstractions of features through the system. And by aggregating them, they were able to make sense of more things. So initially, you can see they look at the lines, and then they look, okay, this is an eye, this is a nose, and then they put that together to be able to do face recognition. Very impressive, right? Okay, so we know that more layers are good. But the question is, how more layers is enough? So They start initially by shallow networks. And deep networks nowadays, when any company or any person says we are using deep networks, they're usually talking between 6 to 8 layers. Well, that's where it's computationally affordable and economically good. And there is a reason for that too, because between like somewhere here, the cost is really good. But when they increased it to 152 layers, the reduction in the error is still good. It's closer to 50%, but wasn't a huge jump enough to justify the cost, which is interesting in itself. Okay, so how many of you now is excited about deep learning? Yeah. Okay, so if you're excited, how can I start? I want to use deep nets. Oh, wow. So the first thing, let's build some foundation. So go read about deep autoencoders, convolutional neural networks, and recurrent neural nets. This is all the basics. If you don't know where to start, look at the superhero researchers. These are the stars of the deep learning field. You have to find an easy problem, but with whatever problem that you decide to work with. It has to be measurable and describable. You have to choose a good data set. Deep learning does work on unsupervised learning methods. However, it's stronger with supervised, so start with supervised. Have a significant computational power, and you have Amazon AWS supports deep learning as well as Google Cloud, and I'm going to talk about them a little more later. And choose a nonlinear activation, and I'll give you a tip. ReLU or ReLU does work really good and yielded very good results. And follow some big companies that are working on this field. This is a very, very, very active field nowadays, and everybody's working on it. And use the right tools. And as you can see, there's a zoo of tools here. So many things. But a lot of them, to our advantage, are actually using Python, which makes it easy for us to use. So as you look here, there are two types of tools mainly. Configurational files, so the ones where you just write a one-page configuration file script, something like Cafe or Disbelief or Microsoft CNTK. So you just do a configuration files and they run. Or some of them are programming-based language, like TensorFlow, Torch, Theano, Deep Learning 4J. And they use different types of programming languages. So for example, Deep Learning 4J uses support, you write in Java and C++. Torch uses a high-level language called Lua. But TensorFlow, Theano, Keras, GenSim all use Python. And I would actually, not because we're in a Python conference, I would actually still recommend these over the others because of the community in the area of, for Python. So there is a huge community with strong scientific libraries, and it's very easy to pick up because Python is a very, very user-friendly language. Interesting. Oh, so I will be talking to you a little bit about Theano and TensorFlow. And my thing is not working. So Theano is considered the granddaddy of deep learning frameworks. It has 4 or 5 years under its belt now. It was first developed at the University of Montreal, and it's used by many, many academics. And this is a key, because a lot of research has been done with it. It's easy to get work to compare with. But again, the maintenance and the support, if you're a company looking into using it, gets a little bit challenging. It handles multidimensional arrays just like NumPy, but there's a little bit of differences between them. And I'll talk to it later. It's an open source, but the nice thing about it, it has some cryptic error messages, not so fun. But the nice thing about it is that it allows that there are a number of open sources on top of it to ease the pain, to make your life easier, like Keras, Lasagna, and Blocks. All of that run on top of Theano and make your life a little bit better. The other very popular library is TensorFlow, and it was created by Google. Some of the creators of Theano moved and started working into Google, and they helped build TensorFlow. So they addressed some of the challenges. It has better user interface, has better visualization, and again, it's based on Python and C++ and C for speed. But TensorFlow is not used only for deep learning. It also allows some other algorithms like reinforcement learning, and it is optimized over Google Cloud, which is amazing. It provides you good speed. However, it's a little bit slower than Theano. And it has its pains. It's a very new language. It's about a year old. So for example, inline matrix operations is not available yet. Hopefully soon, so that makes it a little costly. Still, you can work around it. There are work around it, but it gets costly at some point. So I'm trying here to compare Theano and TensorFlow to NumPy. And because I'm sort of running out of time, I'm going to give you the baseline here. Theano uses NumPy as is. TensorFlow uses NumPy-like operations, but not exactly like NumPy. So it makes it a little bit harder. If you have legacy code that you're working with, especially with Theano and NumPy, it's not totally interoperable with TensorFlow. So pros of Theano: Python NumPy, very expressive syntax, computational graph, has a nice abstraction, so it's easy for you to work with, has high-level wrappers, as we mentioned, Keras, Lasagna, and all of that, and Blocks, and it has a humongous sample code and community, because it was the granddaddy of all of these frameworks. TensorFlow, on the other hand, has similar advantages, but the nice thing about it is that it's started from Google. So the community is changing fast, there is huge adoption, and the code keeps on coming out. So it's amazing. So there's continued support. They fixed some of the pains of Theano, like the cryptic error messages and all of that. But both of them has some issues. So as we mentioned, Theano has cryptic messages. However, TensorFlow is still slower. Google said that they are aware of it and they're trying to work around this and fix it, but at this moment, it's slower. The pre-trained models in TensorFlow is few. However, Theano is really buggy when you start using AWS or big data or multi-clustering, multi-processing systems, which makes it non-scalable. It's good to do some research on it, but if you're a company that you really want to embed with it, you need to start thinking about the processing power. And just a quick overview here. I'm not going to go through this, but I'm just saying that the syntax is a little different. So if you have a legacy code or some code, or you find a library that you want to use using Theano, and you want to move into TensorFlow now, you need to go back and refactor your code and rewrite some of it, if not all, which makes the transition a little harder. So if you are excited about deep learning and you want to start thinking, okay, where can I start? These are some amazing resources. And one of them, and my favorite, and I think you can do it now, and I wish I had the time to show you, is TensorFlow Playground. It's amazing. Let me see if I can. It's not showing. Okay. So it's amazing. It has a visual interface that you can start playing with, add the number of layers that you want. You can see how the performance of your model changes and how is the classification working. So if I'm going to leave you with something, I'm going to leave you with this. Information is the oil for the 21st century, and the analysis is its combustion engine. So we are on the verge of making big things happen. So try to have fun with it, and start doing some analytics. So thank you guys. Thank you. So please feel free to contact me if you have any questions. I know that we have a Q&A now, but if you have any other questions or you want to reach out or ask anything, please feel free to contact me, my LinkedIn, my personal website. Also, we are hiring at IMS, so if you're interested, please feel free to shoot us an email.
All right, we have 5 minutes for a Q&A if anybody has questions.
Yes? Oh, two.
What areas of applications do you find are oversaturated and undersaturated?
Oh, applications? Okay, so I can tell you what I'm working on now from a research perspective, and that maybe gives you some hint about the areas that are not saturated. So, for example, stuff that you're working with ImageNet, I think that's pretty saturated in terms of deep learning. I am actually working on early detection of Alzheimer's and dementia from brain scans, and this area is actually quite open. It's just 2 to 3 papers started applying deep learning into that. I'm using deep learning also in detection of epileptic seizures, and again, that's my research point of view. There's also my work point of view where we are applying it in autonomous cars and connected cars. But for interesting applications, medical applications definitely has a big room for improvement using deep learning.
Hi. My question was really, because I'm totally clueless about this. Do you, is the compute power more important at training time, and then what you produce is a network that can be run, you know, on a normal machine, or is it like we always need to have a giant cluster of machines to make this happen?
That's so much fun. So when I was talking, I skipped this part. So, for example, Google Translate. When you have it on your phone, it's trained once within their huge system, and now when it runs on your phone, it doesn't need internet to run. And it can translate any sentences to 20 languages with no internet, with the processing power of your computer or iPhone. So this is what I'm saying, is that the training and the processing is the heavy part, but as soon as it's done, it's just a classifier, it's just a model that can reside on any system. Thank you. So any other questions?
Hi. So when you mentioned that deep learning is best at approaching when there's lots of little details and you can only make sense of it when you look at everything in the bigger picture. So when you approach a problem, how do you kind of figure out deep learning is the right technique, or if there's other machine learning techniques, I guess, to apply? I guess how do you know like which applications are really well suited for deep learning, and when do you know an application is not really suited for deep learning?
Okay, so deep learning is a new area, right? So neural nets, as we mentioned, has been in from the 60s. It has gone through so many iterations, but in 2006, Geoffrey Hinton started the concept of deep nets, and so it's less than 10 years old, right? As a research area, deep nets especially. There's a lot of work on trying to experiment with all different things. So far, deep nets has shown, or deep learning has shown its power in image, in voice, and so these are the ones, again, so if you think about it, the word in itself, the word is, doesn't tell you much, but coupling it with the words before it and after it makes a sentence and makes it a comprehensible sentence. Same for image, just a pixel doesn't mean much. So these are the applications that have proven to be working really, really nicely. There are areas where if you're just experimenting, I would say try it on anything you want. Compare it to SVM or like something that we know that has good performance, and you can right away tell. I think for me, I try to apply it on multiple unsupervised data, and they showed to be a little bit painful, but I'm sure that with a little bit work around it with it is going to be resolved. So it's a new area. There's not a specific type that I would say no to. It's just like there are ones that are well established that you can just start and run with, and that there are others that needs tweaking, working around, and learning for us. Yes.
All right, I'm afraid we're out of time, so no more questions. Sorry. Thank you, Allaa.